Assalamu alaikum wa rahmatullahi wa barakatuh. Hello everyone. Welcome to lecture 18 Organic Chemistry 3. Terpenes and terpenoids are naturally occurring chemical compounds found in plants and some animals. Terpenoids are emitted by plants for various purposes, such as attracting insect pollinators, repelling insects or other predators, and inhibiting the germination and growth of competing species seeds. In the case of insects, monoterpenes serve multiple functions, including acting as alarm signals, trail markers, aggregation cues, sex pheromones, or even defensive secretion. Furthermore, humans utilize these compounds in multiple ways. They are used to create flavors and fragrances, while also being employed by synthetic organic chemists as chiral starting materials or chiral auxiliaries. Terpenes are a diverse family of compounds with carbon skeleton composed of 5 carbon isoprene units. Isoprene unit is 2-methyl-butane-1,3-diene. Here we have like snake, that's the head, and here is the tail. Okay? And we compare that to the snake head and tail. Terpenoids can be described as modified terpenes, where methyl groups are moved or removed, or oxygen atoms added to the structure. Due to their wide occurrence in nature, all the terpenoids could not be isolated or separated by general method. This is carried out in 2 steps. First, isolation of the essential oils, and then separation of the terpenoids from the essential oil. So in the plant kingdom, step 1, isolation of essential oil, and step 2, isolation of the terpenoids. The isolation of the essential oils could be done by steam distillation, and steam distillation is a process used for the recovery of the volatile compounds with high boiling point from inert and complex matrices, solid or liquid, using saturated or superheated steam as separation and energy agent. In a simple way, here we have a boiler to get steam out, passing the steam into the crude plant. The essential oil will go up and volatile with water and condense it here, forming 2 layers. In practice, the process uses water and or steam as extracting agent to vaporize or liberate the volatile compounds from the raw material. The compounds are volatilized by absorbing heat from the steam and are then transported to the steam where they are diffused. The resulting vapor phase is cold and condensed period to separating the water from the organic phase based on their immiscibility. In this process, 2 products are obtained: volatile oil and hydrosol. The volatile oil is in the upper phase and the hydrosol is in the bottom phase of decanter. According to the type of contact between matrix and the water and or steam, there are three variants of steam distillation process: what we call dry steam distillation, direct steam distillation, and hydrodistillation using water distillation. Here is an industrial plant sketched for the three different processes. If you'd like to read more, steam distillation applied to the food industry, extracting bioactive compounds from food products, theory and application. It's published in 2008, so you can read more on that. But this method employed carefully because it suffers from the following demerit. Some essential oils undergo decomposition during steam distillation. Some constituents of the essential oils, like ester, which are responsible for the odor and fragrance of the oil, may undergo decomposition, resulting in a perfume in inferior quality. So the steam distillation has its limitation. Second method, extraction by means of volatile solvents. This method is widely used in perfume industry and generally used for such plants which yield an oil or give low quantities of oil on steam distillation due to decomposition essential oils. In such case, the plant material is directly treated with light petrol at 50 degrees Celsius. Under these conditions, the oil is taken up by the solvent along with the soluble coloring materials. The essential oils from this extract are separated by removing the solvent by distillation under reduced pressure. Well, we have here container of solvents. We have here succinct extractor with siphon side arm. We have here the succinct thimble, which contains the plant raw material. When we heat up, the solvent evaporates, go up, condense, and dissolve the essential oil, taking up with the siphon back to the container. Okay, and the process continues. Well, if you would like to read more, please go read. And here is using succinate ethanol extraction to produce and test plant material for their antimicrobial properties. Journal of Microbiology and Biology Education, 2014, page 45-46. Read more, and there is a lot of reference in there. The industrial plant will be the same. Here we have solvent gets in, raw material of the plant. Here will get into the concrete alcohol under vacuum. Well, solvent evaporates with essential oil, condenses, and gets into the reservoir. Third method, adsorption on purified fats. We call it Enfleurage method. In Enfleurage method, even the most fragile plants can be used. Depending on the plants that are chosen, the oil or the fat with which the plants are mixed can be heated. It is this oil or fat that traps the plant's fragrance. So like we get pure coconut oil, okay, and then put the plant material on, cover that and leave it for several hours at chosen temperature. The coconut oil will absorb the fragrance and can be used in perfume industry, but it is not longer widely used today, okay, because it getting very expensive method. Another method, carbon dioxide supercritical extraction, which creates phase changes in carbon dioxide utilizing temperature and pressure. CO2 is known as tunable solvent, making it extremely versatile for creating a multitude of end products by controlling temperature and pressure. So here we have carbon dioxide source, pump, and here we have the extraction unit. The carbon dioxide in gas phase through this pump and control temperature and pressure, we can get it in between the gas and liquid phase, goes through the plant raw material, extract the essential oil, go up, and condense it into the essential oil and collecting of the carbon dioxide. The second step is to separate terpenoids from essential oil. One of the reasons is considered to be the oxidation and polymerization of their components, namely terpene hydrocarbons, under the influence of oxygen in the air, moisture, heat, and light. This in turn contributes to an increase in the viscosity and the plane of polarization, to a change in color, to deterioration of aroma and taste of essential oil. Terpenoids are separated from essential oil by either fractional distillation or chromatographic techniques. Characteristics of terpenes. In 1818, it was found that oil of turpentine has a carbon to hydrogen ratio of 5 to 8, and many other essential oils have similar carbon to hydrogen ratio. This group of piney smelling natural products with similar carbon to hydrogen ratios came to be known as terpenes, C5H8N. In 1887, German chemist Otto Wallach determined the structures of several terpenes and discovered that all of them are formally composed of 2 or more 5-carbon units of isoprene, 2-methyl-buta-1,3-diene, connected head to tail as proposed later by Ingold in 1925, known as isoprene rule. So we have here isoprene unit and isoprene unit. They are connected together, head of the snake, tail of the snake here, head to tail connection. To read more about that, Isoprene Rule Revisited, Journal of Endocrinology, volume 242, page R9 to R22, year of 2019. Well, if we have isoprene 2 units, we call that monoterpene. If we have 3, we call it sesquiterpenes. 4 isoprene units, that's diterpenes. 5 cisterpenes. 6 triterpenes. 8 tetraterpenes. And here is an example of the natural products, terpenes. Each class can be further subdivided into subclasses according to number of rings present in the structure. We have Acyclic Terpenoids. They contain open structure. Monocyclic Terpenoids. They contain one ring in the structure. Bicyclic Terpenoid contain two rings. Tricyclic Terpenoids, three rings. Tetracyclic contains four rings, etc. Example of the acyclic terpenoids like myrcene and geraniol. Here is an open structure, as you see, there is no ring. Acyclic monoterpenes. Limonene and menthol, monocyclic monoterpenes, two isoprene units and one ring. Here we have two isoprene units in Thojan and Comphane. So, two rings, it means that bicyclic monoterpenoids. Farnesol, that's three isoprene units, so it's sesquiterpenoids. Acyclic with its open structure. Zenzabrine, that's again three isoprene units. It's monocyclic, which contains only one ring, sesquiterpenoids. Here, cadinine is bicyclic sesquiterpenoids. It has two rings and three isoprene units. Here we have phenol that contains four isoprene units and acyclic, so it is acyclic diterpenoids. Retinol, that's vitamin A, again four isoprene units, it's diterpene, and only one ring, so it's monocyclic diterpenoids. Classify each of the following terpenoid compounds as monoterpenes, diterpenes, and so on. Indicate with dashed lines the isoprene units that make up each structure. Alpha-bynene, well, alpha-bynene is two isoprene units. This is one, and this is another one, right? So, again, here is head, and here's the tail of the other one, okay? So I classified as monoterpene because it contains two isoprene units. Cariphyllene, we can cut in here and here and there. Well, this is three isoprene units. Clear. This is sesquiterpene, right? Sesquiterpenes. It contains two rings. That's bicyclic. Abatic acid. Well, we cut in here, 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 here. So how many? We have four. That's diterpenes, diterpene. Here we have terpenoid structure, cut in here, cut in here. That's what we have, two isoprene units. Two isoprene units connected together with the oxygen. That's monoterpene, monoterpenoid, monoterpenoid. See you next lecture.